type equality from cache.nixos.org, blah, 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 blah.
That's pretty nice.
Yeah. So if it's in their cache, you get the binary version. If it's not in their cache, it builds it locally.
Mm-hmm.
And either way, you're supposed to get the same bits. You certainly get the same package name. And they have kind of 80% of the world's software. Of course, I use Nix somewhat infrequently, and so it downloads everything down to libc every time I go grab something. So you get 0.5 internets every time. Because it's like, if any one bit of any piece of software changes, everything above that gets reinstalled.
Yeah, but you still get full CPU power during that time.
We have downloading, yeah, sure.
Yeah, right.
So that's Nix. So the nice thing, one of the nice things about Nix is you can say Nix shell -p and then wish for a bunch of packages, and then you get a shell with those packages, and then you exit that shell, and there's no cruft left in your machine. You use some disk space, but you can garbage collect it if you want. And then the next step up is to make a shell.nix, which says, okay, whenever I want to work on this project, please install this crap. And this language is a little bit obscure to me. I have to relearn it. I don't use it often enough for it to really make sense, but it's just lambda calculus. I mean, it's just applying functions. The trick is to figure out syntax for where the function arguments are and stuff, and then what the heck do the functions mean. The worst thing about Nix is that they, like if you use apt or something like that, apt is written in C, and you invoke it, and if you invoke it wrong, the C code prints out error message directed for you. In Idris, in Nix, everything is just written in Nix, and if you invoke it wrong, you get Nix garbage messages, right? You get, function 74 on line 93 puked. Not you forgot the -p option, So you get these horrible error messages. So it's that kind of thing. It's great if you have a perfect mental model of it, and if not, you're like, ah. And then the one other doodad I use is this. So if I have completely forgotten about this thing and I cd into this project, then it'll remember everything, download everything, and set all the environment variables, and there we go. So that's what durimp does. Okay, so that's installing 8 levels of software, including Idris. So why do I use the thing? So this friend of mine, Christopher Weber, says he gets math notation whenever he reads papers. The underlying concepts usually aren't so hard, but sorting through the equations makes his brain shut down. When papers provide code, he tends to get through them much faster. And I said, I read CS papers by turning the notation into code, Idris line code. Slow going, but it's the only way I really understand. And then as an example, that's the VS Code thing. So this is kind of the road not taken. This would probably also work, but I'm addicted to Emacs. So as an example, there's this paper. Yeah, got it. On access control and capabilities and confused deputies, where they were doing math notation down here, Greek letters and such. And so the way I understand such papers is I figure one. Figure one, the Regis calculus. Where's a little bit of text? Yeah, values consist of blah, 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 blah. And so has 5 syntax categories. So I just copy a little bit out of the paper. And then I convert it to Idris. So let's do that a little bit slowly. All right. So if you have your editor all set up, then it will do nice things for you. All right, our technical development is based on region calculus, a simple blah, 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 5. Okay, never mind. That's just saying what this module is about. I'm borrowing that part of the paper. Somebody else wrote a library for arbitrary precision integers. And the paper talks about a lattice, but the closest thing I found in the library was order. And then I made up a map notation, finite maps, because the paper wants to use those. I can talk about that in a little bit. Anyway, so the paper says, we assume 2 countable sets, loc of mutable references and prin of principles. Elements of loc are written with a little r, and elements of prin are written with a p. And so for me to make a countable set, I just, nat is the set of natural numbers, so that's a countable set. And then to make a thingamabob that's in one-to-one correspondence with nat, I just said, okay, make a thingamabob called loc, and it takes a nat. So that gives us a countable set called loc. And then loc is injective. That is, if you have 2 different locs, you're going to get 2 different nats, and if you have the same loc, you're going to get the same lat. And so, right, this says that make loc of n equals, if make loc of n equals make loc of m, then n equals m, and the proof is trivial. So these are the sorts of things you can do because we got a nice dependently typed doodad. And the way reflection works is sort of deceptively simple. Yeah, so it'd take a little while to explain, but once you sort of understand the explanation, you're like, what? Oh, okay, x equals x. That's the only way to prove that something, to prove REFL. Yep, we know that x equals x. That's pretty simple. All right. And since it's injective, we can then equality on locs is decidable. And that's a little thing that helps you do that. Again, that would take a little bit of explaining from 0, but those are the sorts of things you can do. And then you can do, this is a pretty typical Haskell style data type. They say values consist of integers, booleans, pointers. So a value is either, I use an int val constructor, and that takes a ZZ that I've gotten from my friend, or the true and the false, those are booleans, read of a loc or write of a loc. Expressions are these, so you just sort of read the paper and translate it. If you're done Haskell stuff, then this is entirely straightforward.
Do you remember why you use ZZ instead of nat there?
Not clearly, but it said integer, not natural, so.
Oh, yeah, sure.
I might have eventually, there might have eventually been a use for negative numbers. I can't remember just yet. So we build up their programming language. And then, oh yeah, one thing that's really inconvenient is when a paper will use the same notation for 2 different things. So here it says we extend the order greater than or equal to on locations to regions. I can't read that little bit. So when blah, 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 blah. And so what I did was I took the greater than or equal to, well, any relation on principles, I can extend it to a relation on regions with this. And maybe making that a universally quantified variable was a mistake. Maybe that should be a constant, but anyway. So that you sort of get the idea, and I didn't get very far on this paper, but basically when I had done this much, I understood enough of the paper to say, wait a minute, this paper is not all that interesting. It's sort of
that just reminds me of like when you're thinking about problems, you know, and then 2 weeks later you're like, oh, it was so obvious from the beginning, you know, but like you had absolutely no idea how to even start solving it at
right.
that beginning, you know. That's funny.
So that's what I use Idris for, is to try to really understand something that I didn't quite understand earlier. You know, because I can sort of, if I just, if I just look at all that, I go, yeah, sure, whatever. You know? And you know, the reviewers accepted the paper, so it must be right, blah, 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 blah. But then I get to the end and I'm like, I didn't really learn anything, did I?
Yeah, so this the Idris that you're writing looks an awful lot like Agda, and I'm not like I'm not 100% sure what all of the differences are. Like, I don't know if they're using different like dependent type systems or whatnot. But I guess out of, well, the three that I know, like Lean, Idris, and Agda, I want to say I'm probably the most familiar with Agda, even though I've really never done any programming. I know you said you like Emacs, but I hate Emacs with a passion, and there's only Emacs support for Agda, which is really unfortunate in my opinion.
Yeah, the differences between Idris and Agda are in a plane of the stratosphere that I have never even visited, I don't think.
Okay.
They're
okay. So you're saying you haven't run into anything that would actually give you any, you haven't seen any differences yet, really?
I can't say that I haven't seen them. I've seen people discuss them with passion, but I just...
Oh, sure. Just not in your use cases.
In particular, there was a bit about least common denominator, which surprisingly needed well-founded induction.
Okay.
And I just borrowed the code from, well, somebody else and I borrowed the code from Agda and went into Idris with pretty much no problem. You can do the same thing with Coq most of the time.
Okay. Okay. Yeah, I'm much less familiar with Coq than all of those.
I think, does Agda let you write partial functions?
Does it let you write partial functions? I'm not totally sure.
That might be a big difference, because Idris has got quite a bit of emphasis on actually writing programs that compute, that are not just to look at and go, ha, isn't it pretty?
Mm-hmm, mm-hmm.
They do grungy stuff like connecting to databases and stuff like that.
Oh yeah, okay.
Yeah, so Idris has like a partial portion to it, so you can like do everything total if you want to, but you can also like hook up to partial stuff.
Okay.
Yeah.
Yeah, I'll look into it. I'm not sure, honestly.
It was meant to be sort of like a general purpose, like a way to use dependent types for programming that you do every day. Now, whether they succeeded on that or not, still working on it. But
it is fun that you can do stuff like, so, okay, here's my, oh, sorry. So if I've got that thing and I want to say frob goes from value to int, and I say frob x equals, and then what is it, case split?
You mean nat or int?
Either way, whatever.
Nat splits in 0 and successor of nat.
Well, but this is value that I'm splitting on, I think.
Oh yeah, true. Then you will split into, yeah, into all the things that you specified structure.
Where is it? Case split pattern. Oh. Wow. So sometimes the tools have rough edges. If I load this thing.
There was I don't know if it's this problem, but there was this thing that if you write just like without a line space between comments, sometimes it complains.
Clearly, okay, so now that's a little
It's super weird.
Sadness. Nothing identifiable under point. I know I have done this. Is it? Oh, well.
You might have to specify a hole on the right-hand side. I don't know.
No, I know it's two keys, and it does it. And anyway, Idris will write about half of your program.
Yeah, one way to do it is exactly, I used to like from x equals question mark what, and then I think you can, yeah, if you compile, they probably you can split on.
What is not a pattern variable? Mm-hmm.
Then there is some sort of problem because that's the whole, and it should be understandable by Idris, no problem. Like everything with a question mark before is just
yeah. Because it's supposed to do this.
Mm-hmm.
And then if I try to load that, it should tell me I'm not finished yet. I've only handled one of the cases. Oh, right. How do you?
Oh, need parentheses maybe.
Yeah. Yeah, so there's missing cases, so
yes.
tell me what they are.
There should be an add missing cases command.
Yeah, is that one? Yeah, no?
There, okay.
Nice.
So. Yeah, the idea is that if once you've told it the type, then figuring out the proofs, the computer helps you with it a whole lot. And there's a whole book on that, which.
Type-driven development in Idris, you mean?
Yeah.
Mm.
And one of the problems at the moment is that basically the whole Idris team is focused on developing Idris 2.
Yeah.
So a lot of bugs of Idris 1 are basically won't fix because they're like, yeah, we'll directly fix them in Idris 2.
Yeah.
But Idris 2 is still pretty much rough around the edges for a lot of stuff.
So yeah. And this is of course all Idris 1.
Mm-hmm.
But he's a researcher, so it's like by the time it's 80% done, he's off to the next thing.
Yeah, luckily enough, I think, I mean, there's a team of students helping him. I think he got some grants for the development of Idris. So.
Right. All right. Now back to our regularly scheduled Rosetta thing. Which so how do I get this thing to show me a list of people? More chat, and again the chat. Okay, stop sharing for a sec. Okay, there it's giving me a list of people. Would like to more directly involve everybody else here. So I'm just going to write down some names. Dan, Jim, W, Steve, H, Isaac, A13PH. What do you call yourself? What should I call you in conversation?
Al or Aleph is fine.
Aleph?
Yep.
Okay, thanks. Craig, have we met?
No, I just came from the category theory Zulip.
Great. And Fab, you're quantifier?
I'm
that's Isaac.
No, that's me.
So Fab is who?
Fab, that's me. I'm the Statebox guy.
Oh, great.
Nice.
I'm not the programmer Statebox guy, so I can be of limited help, I think. But I wrote the monograph, which is the thing we are trying to implement. So I usually basically try to tell developers what needs to be done, and they are able to translate it to working code, and I'm more or less able to follow them, which is amazing.
And should I call you Fab, or is it Fabian, or?
Fab is fine. My name is Fabrizio, but Fab is.
Oh, Fabrizio, that's more fun. Okay. And then I know Jake. And then we have Luke.
Yes, I was here last week.
Okay, great. So I'm going to try to use this little list of names here as like a list of people to talk about the next thing. And you're always welcome to say pass. So when we left our hero, how much did we understand? Let's see. Just for anybody that's here for the first time, bias, stay, that thing. Category, okay, so there's these diagrams. At this point, we have a vague notion of what they are, but this is a really nifty thing. So just to practice here, Jim Whitescover, is your audio, are you participating by audio? Okay, so I might scratch his name. Steve, can you tell us a little bit about this table here? What you took from it, or what you like about it or don't like about it?
We are not also looking at any images.
Oh, joy. Oh, right, I stopped sharing.
Yep.
Okay, so now if I start sharing again, maybe if I can figure that out. Share. Okay. So this was the list of names. Jim Whitescover, are you participating by audio? Okay, probably not. All right. So Steve H.
Yes, I remember this, that table from last week. So with the 5 disciplines that we see, each discipline refers to object and morphism in different ways. So it's essentially the same thing, but using a different word to describe essentially the same thing.
Cool. Pocket version, I like that. So I had to go look up Hilbert space. Let's see. 2.1 background. I'm going to try to skip to one of the more interesting. Oh, this thing. So who's up next? Isaac. Tell me what you do or don't like about this diagram here, or anything about it.
Yeah. So I guess my interpretation of this, and this is more of a question than I know what this diagram is about comments, but so I'm assuming we're saying some sort of like inclusion relations here, right? Like monoidal categories are categories, so we put monoidal categories below categories, and then braided monoidal categories are monoidal categories, so they go below, and closed monoidal categories. Maybe there's not a great comparison between the closed and braided monoidal categories, but certainly they're both flavors of monoidal categories. And then kind of so on and so forth down the line. I want to say I wish I knew a little bit more about what some of these adjectives mean. Like I'm familiar enough with monoidal category, but then I'm not 100% sure what they mean by closed monoidal category, and I'm definitely not sure what they mean by braided monoidal category.
So do you know what a symmetric monoidal category is?
Yeah, so I mean, with your monoidal category, you have a monoidal product, right? Like a tensor product or something.
Yeah, exactly.
And so we're just saying, like, you could do A tensor B, and that's always going to be the same as B tensor A, right?
So hold on just a second. So this is a preview of the paper, is what this diagram is.
Right.
So basically they're gonna tell you what a braided category is and what a closed.
Fantastic. I didn't get to that part yet.
Okay.
Yeah,
yeah,
I think
go ahead.
you will. But anyway, the best way to understand monoidal categories really is boxes and wires. So a category allows you to just put the boxes in sequence if types match. Monoidal category allows you to put them also in parallel. So that's what the monoidal product does.
So wait, what is the box and what is the wire? Like they're talking about here with objects.
A wire is an object, and a box is a morphism. So that thing there is F from X to Y, for instance. And you can put one after the other. And then the idea is in a monoidal category, you can also put them in parallel. And then you may ask, yeah, but in some situations, I need to cross the wires. So basically, I need a way to go from X times Y to Y times X, tensor X. And that's what braided and symmetric do for you.
Okay.
So the idea is that in a symmetric monoidal category, every time you cross 2 times, is like not doing anything. So if you do X, Y, Y, X, X, Y is like the identity.
Okay.
While in a braided, it's similar, but it's like in the crossing, it's like a real knot. It's really, it is important which wire crosses over which other wire. And so there are some compositions that you can untangle, and there are some other compositions of crossings that you cannot untangle, because you are doing 2 things, the same thing, but the wires form a knot at that point, and you're not able to disentangle them. And then there are a lot of other flavors that do different things.
Cool. Thank you so much for that explanation. That really kind of clarifies those.
That was the whole paper. We can all go home now.
Well, okay. Let me ask my stupid question in response to that, because so when you say in parallel, you're talking about this diagram here, kind of like the one with actual pictures, right? There's like
yes.
Okay.
Yes.
Okay. Perfect. Cool. Okay.
Exactly.
That totally makes sense.
So the best way to, I think this is one of the perspective they use in the paper, but the best way to think about this stuff is like systems and things you can do on systems. Yeah. So you can have a category of recipes where your objects are ingredients and your morphisms are things that turn ingredients into other ingredients, like carrot, peeled carrot, for instance. I don't know. And then the idea is that, okay, but I can also chop the potato while I boil the tomato, and I can do this thing, the things contemporary at the same time. And then that's why you need a tensor, because then you can describe, these operations happening at the same time.
Okay, so then do people use these either symmetric or braided monoidal categories to talk about concurrency? Is that kind of the idea?
Also, well, you are tapping a very deep line of research because it turns out that Petri nets, which are probably the most studied tool in concurrency, are presentation of symmetric monoidal categories.
Okay.
So there is a very deep entanglement between stuff that is traditionally done in concurrency, and this stuff can be the categorical semantics of that. And then the other super big field where actually all this stuff originated is categorical quantum mechanics. So that's why they also do all these Hilbert spaces kind of thing, because it turns out that this is a very convenient graphical calculus to express a lot of stuff that you would do in quantum mechanics using horrible linear algebra. And so you can hide all that stuff basically and just talk about quantum protocols without having to go through humongous matrices of stuff that
so you're kind of hinting at like Feynman diagrams there, right?
I'm more hinting at the work in particular of Samson Abramsky and Bob Kuke. Yeah.
Okay. Okay.
There is this very, very, very nice book that is called Picturing Quantum Processes. It has been named multiple times in Zulip. And that just teaches you quantum mechanics completely with diagrams.
Oh, whoa, slow down. What book? What? That's the thing I need.
Yeah, it literally teaches you. It's 800 pages. It's all pictures, so it's very easy to read.
What are the Google keywords by which I can find this
Picturing
thing?
quantum processes.
Yeah. Picturing quantum processes.
I want to say Greg mentioned this book at one point in time.
Yeah, that's by Bob Kuke. That, by the way, was my PhD supervisor. That's why
cool.
I know this stuff. And Alex Kissinger. And yeah, basically they do everything with diagram. And the reason why it works, that's the whole point. The reason why this quantum mechanics with diagram stuff works is because each one of these diagrams is actually the graphical calculus of some flavor of category, which incidentally is exactly the right flavor of categories to do Hilbert spaces and all the linear algebra stuff that people do in categorical quantum mechanics, in quantum mechanics. So you can forget about the matrices and stuff and just use pictures, which is great.
I think there's also a reading group that's meeting every other week on Sundays. That's kind of maybe on chapter 2, I think now, that's meeting, discussing this stuff. It's a spawn off of the NYC category theory meetup that's all virtual now. So I can give details to that later.
Well, I think I might have some hope of reading that book just by reading it. Anyway, yeah.
Just to give you an estimate, when I was TAing for this book, the course that this book was the book of the course, Bob would basically do 100 pages per week. So that should tell you how quick you can progress on this book. It's literally easy to read. It seems intimidating because it's very big, but it's actually very easy to read.
And on the stuff about parallelism and stuff, this is some paper that Greg mentioned, changed his life or something. So it's still on my list. I haven't read it yet.
Oh yeah, Samson Abramsky's paper. Yeah. I've tried to read it. It was about a year ago. I wasn't ready to see these ideas yet.
Right.
But maybe it's time to look.
Okay.
I mean, Samson is a genius, so there's no doubt about it. Every time, I just found out that he worked 30 years ago in something, and he just said the most amazing and useful and important stuff about that something, and then just started doing something else. I'm like, what the fuck? How is that possible? He invented categorical quantum mechanics, but it also developed domain theory with Dana Scott.
Right.
Yeah. So it's a combo of life achievements.
All right, that was a success as far as this discussion technique.
There was a chat. Oh, okay, never mind. Answered.
Right. I asked a question about this, and we went everywhere, which was great. Okay. So I'm going to skip past that one a little bit. Isomorphism, inverse.
Isomorphism just means that basically if you compose something with its inverse, is like doing nothing.
Right.
I can.
There's somebody in our chain whose Discord name is Cobordism, because I have a loose understanding of that, and most of us did last week, as I recall.
Yeah, that's the swarm guy. Forgot his name.
Aleph, do you know anything about cobordisms?
Sadly, no. I have vague intuition just from the text, but nothing in words.
All right. Any other observations on this bit of, let's see, sort of the whole, I guess a lot of people have come at categories from a lot of places. So if you're here, you're not seeing categories for the first time, and morphisms and isomorphism. But so for example, Hilbert space, I either didn't know or forgot it. I went and looked it up, and it's not that big a deal for me anymore. Any other sort of, or tangles, those were new to me. Any other kind of observations or questions about this section, Aleph? Now, you weren't here last week, right?
No, I haven't been here last week. It's actually my first time participating
Okay,
here.
great.
Actually, I've read this chapter way before and sadly I hadn't time today to reread it.
Okay.
So I may be quite a bit useless today, but I'll get along.
Okay, and it's always fair to say I'll pass.
Well,
so, what do you remember from when you read stuff before?
Well, I remember when I've read this paper, basically skimmed first some pages of it. My biggest takeaway was, oh yeah, so category theory is really useful not just in those fields of math. I was like familiar that it was used in topology, in some like algebra stuff, but here are other not quite as mathematical fields which can use categorical language and which can be used as, well, translation source or target, which is the name of the paper implies. And that really opened me up to the applicability of category theory, and here I am from the ACT Zurich.
Great. Good to meet you.
I'd just like to add, jumping off from the word cobordism, which I've never heard before, anything in this paper which is specific to topology is immediately going to go right over my head where it's not juxtaposed with one of the other fields.
I'm still learning names. Who was that speaking?
This is Craig.
Okay, great, Craig. Yeah. Yeah, I suspect that if you pick anybody here at this call, we're going to be somewhat familiar in 2 or 3 of the disciplines, and the other ones are new to us and stuff like that. Certainly for me, quantum mechanics is like this huge elephant that I've touched the toe of or something. I had a course in topology, and I've remembered a little bit of it, but that was many years ago. So anyway, we didn't do any tangle stuff. It's all about.
Yeah, I mean, the idea is that also if you try to do category theory by reading the MacLean, which I think is the best approach, but many people would say it's not, it gives you a lot of examples in a lot of different fields. And the point is that you are not meant to understand all of them. Like it gives you example from algebra, analysis, geometry, and the idea is that you are probably familiar with at least, one of the things that it presents, and so you can understand the categorical concept. So it's not really a problem if you don't get topological examples, just like there are just other examples of the same concept, so you can just like not care about.
Yeah, what I'm starting to absorb is that what you should understand from those examples is the sort of the categorical level of it. It's kind of like, well, an orange is like a sphere, even though I don't understand all of the cell level biology that's going on in there.
Precisely. So category theory is the study of patterns. So the idea is that you want to capture a pattern that happens in mathematics or in physics or whatever, and then you have a lot of things that are an example of this. But yes, what is really important is the pattern, it's not the example itself. So yeah, these tangles things are basically knots, as you can see. So it's literally.
Okay. I'm gonna. Okay, functor. I don't think is, all right, monoidal categories. So if I picked on...
Functors is really, I don't know if you already went through that. That's a really important concept.
It's certainly important.
I can say what functors and natural isomorphisms are.
Sure.
Because I'm Aleph. I'll tell my name so everyone
Great.
remembers. Basic terminology for category theory is object and morphism between those objects. And functors are basically like morphisms are for objects. Well, functors are for morphisms. Those are morphisms between morphisms, if you want. And natural transformations, if I remember that correctly, I'm sorry. They are one step higher. So they are basically functors between functors. So they take you not just from one category to itself, but between categories, if I remember it correctly.
Between functors that can go from different categories.
Yes, that's kind of what I was getting at, but yeah, thank you.
I think the best way to understand natural transformations is that imagine that you have a category C and then you have a functor to another category D. So what this functor is literally carrying the relevant structure of C into D, and that's why it's important. Now you can imagine that in D, you have a diagram where everything is the image of a functor. So you have like f of x, f of f, f of y, f of g, and everything has an f in front of it. And so everything is being the application of the functor from the category C to the category D. Now you say, okay, now you have another functor from C to D, call it G. How can I replace every F in this diagram with a G? And it turns out that the way you do it is exactly if this square that is depicted here commutes between F and F prime. So the idea is that if you have one of such squares for everything, then you can take a diagram which has F everywhere and just write F prime instead of F in that diagram. And that diagram will still commute. So you can basically rewrite F prime instead of F. And that's the relevant idea of transformation when you study functors, basically. So then.
Yeah, what I'm starting to get is, at first there was these pictures, I'm like, well, so what? You can draw a bunch of symbols and with arrows on them, whatever, but there's, implicitly you can turn these into equations. So that's starting to make sense to me.
Yes, exactly. And what it says is that it doesn't matter which path you pick.
Right.
If you go from f of x to f prime of y, every path gives you the same thing. So yeah, you can turn it, if this was in set, for instance, this would exactly be an equality of functions. You would say that the composition of f with alpha y is the composition of alpha of x with f prime of f. So yeah, diagrams are exactly equations.
Craig, I guess I'm just meeting you. I don't know how much of this you've read or if you have any thoughts on monoidal categories or questions.
Well, we've already been talking about them to the extent that I'm familiar with them.
Okay.
Where you can draw two boxes in parallel because you're combining the two categories with this little tensor product X in a circle.
Right.
I haven't read the formal definition though.
It's pretty much what you just said.
And I've seen this triangle equation before in, what is it? Category theory for programmers, where it's sort of like the Haskell pair function. I think I read that some people here are programmers, and then turning the arrows backwards is, oh no, it's not quite how I remember seeing it. But I feel like if you turn the arrows backwards, then it's called a projection from XY to X. No, that's slightly different. Forget what I said. Sorry.
It's all right. Yeah, I guess the only wrinkle to it as far as just being regular pairs is that there's this thing that makes it so that it doesn't matter which way you pair them. They associate.
Yeah, Haskell is a more or less a Cartesian category. So you've got this the projection, but you don't have them in general in a monoidal category.
Yeah, the main difference is that in a Cartesian category, so when your monoidal product is a product, you can copy things for free. So if you have X, you can always go from X to X times X, and you can forget things. So if you have X times Y, you can just get X out of it. And as Luke says, that's projection. And these are two things that are not true in arbitrary monoidal categories.
Right.
I have a question about point 4, the natural isomorphism associator. Does that give you an isomorphism in the product category of C and C, or an isomorphism in C, or both?
So that's a morphism in C. So you're saying that for each X, Y, and Z, you have a morphism in C from between these two things.
I think he's asking about this part.
No, I'm not. The point right above. Yeah.
Yeah,
I'm sorry.
that one.
Okay, so
Yes,
that's a
I see.
morphism in C. Yeah, I guess just the notation in the paper didn't make that abundantly clear. Could it
Yeah.
also be a morphism in the product category?
Well, if you consider C times C and you have a monoidal structure on C times C, I guess yes. But in general, the tensor product is a functor that goes from C times C to C. So it takes two objects of your category and gives you again one object of your category. So when you write X tensor Y, X and Y are in C, and X tensor Y is as well in C. So the point is that all these objects in point 4 are stuff that lives in C. Does it make sense?
Yeah, that does make sense. Yeah, I guess going into a little bit of the motivation, I was looking at in this implementation in Idris, and I was a bit surprised to see that essentially like compiling all the way down to an isomorphism in just C, I expected the associator to give you an isomorphism, essentially like only taking away one set of parentheses and not both of them, if that makes, not essentially like only computing one of the products.
What do you mean precisely? Like,
I guess if I could share my screen quickly, I can show you precisely in code. So I think I was expecting a natural isomorphism where your first category was, where the first functor was a functor between
oh, now I get what you
product
say.
category, cat, and cat.
So the problem is
Yeah.
that this is not just an isomorphism. This is a natural isomorphism. And that means that it's a natural transformation. So its actual types are functors. So that's exactly why it's like, yeah, it is as you say, this is a natural transformation between, like if you do product category is a functor that goes from cat to cat. So
Yeah.
I'm doing it 2 times and I'm getting another functor. So these 2 things here are 2 functors. And so that's why this is the type of natural isomorphism. What
Well,
John
so-
Baez is showing you on that paper is just the components of this natural isomorphism.
Right. Okay. So yeah. So then this is how it's actually implemented by you.
Yes, because when you do stuff in Idris, you have to be like very careful and just give the types correctly. And yeah, I was about to say that the definition on Rosetta Stone exactly obscures the natural part, which is super important, because it's not just that I'm giving you an isomorphism for each 3 objects, X, Y, and Z. I'm giving you a natural isomorphism. That means I have a consistent way of picking these things for each 3 objects across all the possible choices of 3 objects. So that's a very important point, because if you just have isomorphisms that are not natural, you don't have those commuting squares we were looking at before, and then you don't preserve compositions, and basically everything falls apart, and then you can't do anything.
Okay. So
I think part of the confusion is because correct me if I'm wrong, but in that definition of natural isomorphism, the first type and the second type are not the starting point of the associator. There's a starting and ending point of the functors between which the associator is isomorphism.
Yes, precisely. Yes, exactly.
So I guess that's what you're confused. Like the second cat says that the associator is a natural transformation between functors from cat times cat times cat to cat.
But by the way, yeah, that shouldn't be cat. That should be product category. That should be the thing that was there before.
So that might be the reason why, because this is how it's implemented right now. So I'm wondering if changing it to this might fix some problems.
Well, I mean,
or do you think that's not correct?
Yeah, because if you look at the paper again, you've got that the associator is a natural transformation from something that takes 3 objects of C. So the source of the functor is indeed the product is cat times cat times cat.
Oh.
And then it applies the monoidal product to the first 2 of those 3, and then the monoidal product from the result to this one. So this functor goes from cat sin cat to cat. So it's a functor that goes from like cat 3 times to cat. And then you've got the associator, which is a morphism between those 2 functors.
Got it. Yeah. Okay, that definitely, thank you for helping clear that up. Okay.
I don't remember now how we defined the natural isomorphism precisely, so that's probably why I'm getting confused. But yeah, what you say is correct.
So then, so then these are your actual functors. I can go back and look at that, but I think then.
I mean, we implemented this stuff, I think, roughly 1 year ago. So, yeah.
Right. Okay.
I don't know how powerful Idris is in that kind of thing, but you could probably let Idris guess them, because you give the explicit functors, so the information of the source and start types are present.
Mm-hmm.
Yeah.
Yeah, that should be the case.
Okay. I think I'm convinced, but I need to go back and look at it again. Yeah, thanks. Oh, so you were saying though that the second, okay. Yeah.
I can't see any more share screen, so I don't know.
Okay. Yeah, I guess I don't think I have anything more to share, but yeah, thank you.
Cool. Maybe I'll share just for a sec here. Luke, do you have a favorite part of this thing or a question? Or
your
Not
screen again now.
really. Up till now, it's been definition. I read applied category theory a few months ago, so it's mostly been definition I was familiar with.
okay. Let's see. I don't remember how far we were supposed to read this week. Jake,
We're supposed to read through closed categories.
Trying to remember how much I read. So, okay, where braided? Yeah, I remember that to some level. I remember reading it. Symmetric. Yeah, we talked about that briefly here. Oh yeah. Yeah, closed. This is where you get the lollipop, huh?
Yeah. It's one of the way of denoting the home object, yes. Not the only one.
The exponential is another, right?
Yes, the exponential, or also some people denote it with square brackets.
Okay.
I guess it depends on in which crowd you are. So if you're working with pre-sheaves, it will be almost always exponentials, I guess.
Okay, so the lollipop in set is a set of functions. All right.
Yes.
So this is currying, I think, which is the example that makes the most sense to me. You can take a function of x and y, apply an x, and get a function of y.
Precisely. So the reason why they use the lollipop here is that, again, your category is monoidal. So when you talk about a set of functions, you are considering more than anything else like an exponential. And an exponential is the lollipop when your monoidal category is actually a Cartesian product as a monoidal product. And okay, so the main, I don't know if anyone here is familiar with classic logic and linear logic, but the point is that the difference between these two flavors of logic is that in linear logic, you cannot copy resources arbitrarily. Right. So, in classic logic, I can say dogs have 4 legs, and I can use this statement in a theorem as many times as I want.
Right.
While in linear logic, statements are treated like resources. So if I have dogs have 4 legs and I have it only once, after I use it, I don't have it anymore. And that's why basically the point is that monoidal categories are a model of linear logic, and while Cartesian categories are a more model of classic logic. And that's why in Cartesian categories, you can project and you can copy as you want, because you can forget about assumptions, you can copy them, while in monoidal categories, you cannot. And that's exactly why they use the lollipop, because the lollipop is the implication in linear logic, which is, in the case of the tensor thing, being the Cartesian product, this reduces exactly to like the set of functions. And that's also the main intuition behind these things, because the idea is that if you have two sets A and B, you can consider functions from A to B, and this is a set, right? So the category of set has an object that represents the morphisms between the objects. You following me?
Yeah, yeah.
So that's what you want to say. What you want to say here is that there is this object X lollipop Z, which is the internal representation of hom XZ. So if I write hom XZ, I'm denoting all the possible morphisms from X to Z, for instance, but this is not an object inside the category.
Right.
So you are internalizing, that's the key word to describe this thing. You're internalizing that object, having a correspective of it inside your category, which is the lollipop in this case.
Right, which in Idris is the type, function type from X to Z.
Yes, exactly, precisely.
Yeah. And because you can write that type. Yeah.
Yes, and you can, I mean, in Idris, obviously, and I think also in Haskell, the actual category you are working in is set. So I think you can always copy stuff, basically. But
yeah,
yeah,
they call it something else, but it's definitely the case that from A, you can get A and A.
yes. And exactly the, you know, in category theory, you want to define everything up to universal property. And the idea is that the universal property that characterizes this internal home object, so the lollipop, is exactly curring and uncurring. So that's exactly what once you require this natural isomorphism here holding, then that's what defines the lollipop precisely. So yeah, for instance, an example of genuine lollipop is with Hilbert spaces, because you can say that the space of linear applications from a vector space X to a vector space Y is again a linear application, because you can sum them and you can do the scalar products of a linear map, basically. So linear maps form a vector space. And in the case of ILB, that's exactly what you have. X lollipop Y means the vector space of all the linear maps from X to Y. So for instance, if X and Y are R to the N and R to the N, then the lollipop XY would be the space of all the matrices having N times M entries.
Right. Okay, now I'm starting to get fuzzy. I'm not sure if I read all these words.
Yeah, and this is also where it gets fuzzy too, because like with the cup and the cap, the unit and the co-unit, those aren't really things that we get in our programming languages.
It's the cobordisms again.
Right?
Like I've checked up the Wikipedia page and freshened up my intuition. That's basically like having a hot knife and a glue. You can make straight cuts in figures and glue them together, or something like that at least.
Mm-hmm.
I think in Rolang, we may very well get cups and caps. It's a, you know, I'm not certain about this, but in pi calculus things, as opposed to lambda calculus things, this stuff, when you do the Curry-Howard stuff for pi calculus stuff, you get lollipops and stuff, and not you know, in other words, you can't go from A to A and A. That you don't get that for free.
Mm-hmm. Yeah, but I mean, closed monoidal is not necessarily compact closed, though. Like,
Oh,
even
sorry,
if
I didn't realize I skipped into compact.
that should be, yeah. Oh, they call it. They are using a very, yeah. This is closed categories, right?
Yes, I use the example of closed category to introduce the notion of compact categories.
Okay.
So they start by saying that, hey, look, in that specific closed category, the home object is actually the product of something times something else. And if that something else always exists, then we can speak of compact categories.
Yeah, but yeah, I do agree that the reason why cups and caps are difficult to get is because they aren't present in Idris or in Haskell, and that's because the category of sets and functions is not compact closed. So you don't have the caps and the caps. The real idea between these cups and caps is that you can turn inputs into outputs and vice versa. So necessarily when your category is compact closed, that means that there isn't a precise sense of directionality. So for instance, functions are very directional because you have this idea that, you can send every element to exactly one element in the codomain. So like you can have X and Y corresponding to the same Z, but X must correspond to exactly one Z. You can't send one thing to two things with a function. While in relations you can. So like if you have sets and relations, then you can say X corresponds to Z, Y, whatever I want, and there isn't this clear distinction anymore. And in fact, you can reverse things in relations.
Right.
Which even the concept. If I say X is related to Y, then clearly Y is related to X. You can
Right.
go. And so these things here allow you to turn inputs into outputs. And in particular, you have that, for instance, a relation from X to Y can also be thought as a relation that goes from nothing to X times Y. So this is because a relation is just a subset of a Cartesian product. So what you say is that I do X times Y and I take some pairs of this set. And I say that this is my relation. And that's exactly the intuition. I say that a relation from X to Y is a subset of X times Y. That means I can plug a cup, turn the input into an output, and now I have something that goes from nothing to two outputs. So it's exactly something that is a relation that goes from the one element set, which we don't draw as a wire, to the Cartesian product. So it's exactly picking a subset of this Cartesian product, basically. I don't know if this makes things clearer or more confusing.
A little bit clearer.
I was wondering if then, because I mean, we can obviously represent these things in Idris and we have relations, but I was wondering if, and I don't know enough about like the numerical type theory or this idea that you can have types that exist if they're inhabited, but to me, they kind of felt like they had a little bit of a flavor that might allow you to do this kind of thing where the types sort of like annihilate each other if when you pair them together, they're uninhabited. Like you can't have something that satisfies both properties at the same time. And at least that would be a unit. I don't know what a co-unit would be, but I don't know. And I might be totally barking up the wrong tree there, but I'm wondering if anyone has thought about that.
In Idris too, they have some idea of linear types where you can use all of your instances of a variable and then you can't use it in the function definition. As in, if you're given something, you can only use it once on the left-hand side and right-hand side of the brackets. And you can also have an empty type, which is like an unprovable proposition, which you could have as a prerequisite, which isn't useful on its own. But if you say, like, is this number greater than 2? And then the options are to either pass the unit type or the empty type, you can have that and sort of disallow certain conditions. I'm not sure if that covers what you're asking.
Yeah, I guess, yeah, I was wondering if that sort of stuff, that's cool. That actually gives me a little bit more flavor into it than I had seen. But I was wondering if you can relate any of those types of things, any of those types to cup and cap in any way. Like, are you somehow turning your type system into something that is closed and compact in a way?
I have no idea about that. I didn't read this chapter beforehand.
Sure.
So I'm trying to catch up right now.
As I say, the best way to understand this chapter is try not to think about certain functions because they don't satisfy this property. So
right.
For instance, another example of a compact closed category is vector spaces. Because again, they don't have a clear flow of directionality. Things are reversible. Unitary transformations are reversible. You can go from one to the other and go back. I'm trying to remember which thing was the, yeah, so the idea is that you can represent a linear map from two vector spaces as a matrix, you know, with, suppose you fix a basis and do all the stuff you have to do. Then you have a matrix of n times n entries. But then, since as we said, these matrices form a vector space by themselves, then I can say that the linear application from a linear map from X to Y is equivalent to have a linear map that goes from R, the one-dimensional vector space, to R to the n times n. So it's exactly saying that fixing a linear map, it is the same thing as picking a matrix, and you obviously are picking the matrix that defines that map. And that's what the COP is doing for you in this case. So what you are actually doing is you are turning your input into an output, and you are taking an application that is actually spitting out all the couples of vectors that are related by that linear map. And on the contrary, if I give you all the couple of vectors that are related by a linear map, you can reconstruct the linear map from this information. So you can always go back. And that's what the snake equations give you. They say that if you turn an input into an output and then you turn it into an input again, that is like doing nothing. It's like, you know, you can strain them this wire and say, okay, you know, like that here on the left, you're saying, okay, I have from this is a top to bottom, yeah. I have an input and I turn it into an output, and then I change my mind again and I turn it into an input again. Then it's like just having the wire. So it doesn't matter how many times you bend them.
Do PatriNets allow this sort of thing?
No, normal patronets don't, but we actually wrote a paper about this. There are patronets that present free complex closed categories, and those are patronets where you also have negative tokens.
Oh.
So imagine that you have also negative tokens, and the idea is that every time you have a negative token and a positive token, so a normal token in a place, you can annihilate them. So draw one as black dot, and the other one as a red dot. The idea is that when you have a black and a red dot in the same place, you can erase them. Yeah. On the contrary, you can always produce a couple out of thin air, because it's like saying 1 plus minus 1 equals 0. Every time you have a 0, you can rewrite it as minus 1 plus 1. So in any place you want, you can make appear one of these couples. And this appearing thing is the cup, and the erasing thing is the cap. And that's exactly, I can, wait a second, I'll just link you this paper, and because there is an image that actually makes a lot of sense there. To make understand this thing better. So the paper is this one. It's in the chat. And if you go all the way to page 137, there is a big picture. I don't know if you can see it. That's exactly the correspondence between monoidal categories and complex closed categories and these weird patronets.
Can somebody else share it? I'm struggling.
I can share the screen. Yeah, it's not a problem. My computer is not super nice when it's about sharing, but can you see this?
Yeah.
So the idea here is the following. I have this patronet here, and I have a token in X. And now I am performing this operation tau. And you know, in the corresponding categorical word, this is like I have an X and I apply a tau morphism now, and I have a Y. But then X is empty, and I mean, I can decide to produce a couple of token and anti-token in X. And this is exactly drawing the cup here. I'm drawing diagrams left to right, by the way. And you know, now I have a token and an anti-token, let's say. Cool. Then I move the black token to Z, and that basically just means applying this V new, actually is a new, this new morphism here. Then I do mu, and you know, I carry the token from Y to X. But now I have again two tokens in X that I can erase. I do that and I get a cup. Now the interesting thing is that because the snake equations hold, this is exactly like, you can straighten this wire, and what you get is that you have X, then you go to Y, then through tau, then you go to mu, through mu to X again, and then you go through nu to Z. So the idea is that you can visualize in this particular example, this red token as a sort of debt. It's like saying, this X is like, this red thing is like a promise. Like I'll promise you that I will give you a resource of this type at some point. And indeed, as soon as you can provide one of these resources, you can put a cap and close this thing and straighten it. And then you obtain a computation like this red thing never happened, basically. I don't know if this makes sense. But.
Yeah, or if you consider these somehow like parallel processes that can do like other things, right, other than just morph these around, then you're essentially getting somewhat of like a free distributed algorithm for doing that, right? Yeah. You're getting, yeah.
And you know, you can also see, you can use this thing to see that, where is it? Here, I think, yeah. Now I want to prove that red tokens actually flow backwards. So if I have a transition from X to Y, I know that black tokens go from X to Y, but I want to prove that red tokens go in the opposite way. How do I do it? Well, I can produce a couple here in X, and I do, and then I can use tau to, you know, get the black token to Y, and then I erase it. And again, since I can straighten yank this thing, this is like carrying X, Y at -1, so the red token to X -1 to the X. So this is a graphical proof, a totally legal, formal proof that red tokens flow backwards in these patterns.
Right.
And you can do it exactly because you have these yanking equations around.
If I may, before that picture, basically, the best the one with flowing backwards, if you can focus it, please. So before that, my best intuition for, well, snake was actually pairs of particles and antiparticles, which is very strange. I am not that good in physics, but still. Especially those kinds of physics. But now, if I may share an intuition, it's like the convention of which direction the electricity flows in a wire. We can say it flows from plus to minus. We can say it flows from minus to plus.
Yeah.
It's just a matter of convention. And whether we consider electrons themselves moving, well, they move in a very particular direction. I'm sorry, I will not remember which one. And if I remember correctly, holes, well, they basically flow in the opposite direction.
Yes, precisely, yes.
So this is a very universal representation for this kind of intuition.
Yeah, indeed, we had this thing because at some point we were thinking that if we could make everything more complicated, we could probably obtain something like Feynman diagrams at some point. But then we got bored very quickly and never really investigated this thing further. But yeah, I think we basically wanted this thing because in our applications, you know, if you run a patronette on a distributed system, and this is this example here, it could be that, you know, someone consumes X, but then someone else that is out of sync does new at the same time, and now you have a problem because this token has to be in Y and Z at the same time. You know, like I maybe do tau and someone else does new at the same time, and by the time all these messages are broadcasted to the network, you have a conflict basically. And instead what you do is that you can just create these depth resources, and then you have to spend them to resolve the conflict at the latter stage. And then you can basically get rid of the red tokens. That was the intuition that in the end brought us here. But yeah, anyway. I do agree this may be useful in physics in some way.
And if I can share another thought, like in practice, what I think, like it's coming from applying category theory to life and business and stuff. For me, it seems like one of the approaches would be to choose what kind of categories are proper for your, for example, business, and choose what kind of well, executable model, if I may say so, is the right one. Because like with those Petri nets, well, heavily modified Petri nets, yes, you can choose something else which will give you the same result, but not only visualization will be different, but various performance and other parameters. Is that how you were approaching it, or do you have any like insight opinion on this take?
Don't know. I have to think about it, I guess.
I guess that's good.
I got to run along. And I haven't really figured out what we'll do next week, but we'll figure it out, I guess.
Mm-hmm.
Yeah, sounds good. We can figure it out and post it in the chat.
Thanks a bunch for coming, Fywood.
You are
Thanks.
welcome. In any case, maybe next time just ping me if you are doing some Idris, and I'll try to, because I think it can mainly be useful to, you know, navigate through the code base if there's need. Yeah.
Sure. Yeah. Thanks.
All right. Bye for now.
Thanks,
Bye.
guys.
Bye.
Bye.